Okay, so let's get started. In a previous video, I made this with Google AI Studio. It's basically a simulation of the birth-death catastrophe process. And you just press the button and it redoes the 10 simulations, or you can change the catastrophe rate, so on and so forth. Okay, but this is just one Markov process, the birth-death catastrophe process, with just those 3 transitions. Now, I have a vision of something like this, but instead of it just being one simulation process, you can sort of, as in Desmos, where you write a function, you can write your own Markov simulation model, or Markov model, arbitrarily. So the idea is, instead of it just being the birth-death catastrophe process, you can make it the birth-death process, or the Poisson process, or you can make it a 2-type Lotka-Volterra process, or you could make it any sort of arbitrary Markov process you want, just by inputting a few details in some sort of UI, and then running the simulation. So that's kind of the ambition. That's what I want to try and make. And this video is just a log of my current progress in that direction, because at the moment I've got a bunch of different code files and they all do slightly different things, and I just want to have a record of what each one does so I don't forget, because it will be confusing if I look back on this in a couple of weeks and I have forgotten. So I'm just going to go through these files and briefly describe what they do. Okay, so the first file is just a basic Gillespie simulation of the standard birth-death process, and I think this is just, I just pulled this from my old files from during my PhD, and so this is just a simple birth-death process, and it simulates standard birth-death process, nothing complicated, and it uses the Gillespie algorithm with uniform random, then it generates the time till the next event, and then it just uses this if-else statement to choose which event to execute based on the rates, the probabilities based on the rates. Okay, so what I did from here is I went to Google AI Studio and copied and pasted that code and said, firstly, do you understand what this does? Do you know what a Markov chain is? Yes, okay. And then I said something along the lines of, suppose Markov chains are defined in this particular way. I'm just going to write how I wrote it at the time, something like this. So a continuous time Markov chain can be defined by a collection of possible transitions and associated rates, defined like this. So just making sense of this, there's x and y, which are like 2 values of the Markov process. So the process is like x, t, y, t, where x and t vary over time. And so in a given interval, short interval of time, delta t, between t plus delta t and t, there's some change in x and there's some change in y, defined by xc and yc. These might be 0, but the rate at which this happens is defined by this function f xt yt, and that can be defined any which way. In the birth-death process, it would be something like lambda xt for the birth in x. And so I said, going off the basic Gillespie algorithm code, Can you come up with a way of writing a program which can run any Markov chain of this format with user inputted transitions and rates? Okay, and it did something along those lines. So if we just go back to here. Okay, so general continuous time Markov process attempt 1. And it came up with the solution where you define a transition class. So each transition has its own class object, and there's like this change value and there's this rate function. So the change is the like plus or minus in x and y, and then the rate function is the f. Right, and so the transitions are added here. So transition is defined, define in this case the Markov-Volterra model, and there's a list of transitions. Each transition is defined as the class object, and there's a change, in this case +1, 0 for 1 pre-birth, 0 predator deaths, and the rate function is pre-birth rate, and pre-birth rate is defined as a lambda function. So this is just a way of defining a function in one as an object that can be put somewhere, if you like. It's similar to the I just learned properly about this today. In JavaScript, how you have the arrow function. So the lambda function in Python is like the arrow function in JavaScript, where you can define it as an object and use it in different places. So it's just a lambda function with the variables x, y, p. Okay, and x is the state. P is a dictionary of parameters, and so it's in this case p alpha is being used as the birth rate, and then so the model is defined as this list of transitions. These transitions are returned, and then transition model, and then the Gillespie general xy function is called with that list, and this is it. So while t is less than t max, get the time till next event, and then probabilities of the events happening, and then transitions, chooses a chosen transition, and then state is changed by the chosen transition dot change object value. Okay, so in principle with this, you should just be able to add a new line and define any of the transitions and the rates as you like. So in theory, for any homogeneous two-type Markov process, you should just be able to simulate it simply with this code. Okay, so that looks good. That's the Markov-Volterra model. It's a stochastic Markov-Volterra model as a Markov chain. And so after this, this code is kind of long and there's lots of comments. It's 200 lines long. So I copied and pasted that into Claude. And I don't know if the chat's saved, but copied and pasted it into Claude and just said, take this code and make it smaller. So can you minimize this code to its core functionality, but make sure the code is presented in a way that is easy to understand with minimal comments to help someone know how each part works. Okay, and it did that pretty well. So it went from 200 lines to less than 100 lines, and it does the same thing. And it's written slightly differently. The transitions, so the functions are actually written into the transition lines, the transition definition lines. And it's just a bit neater and smaller. Same process though. Okay, but then there's one missing part of this, which is, so we want the birth-def catastrophe process to be one of the possible things that you could simulate, and not just the birth-def catastrophe process. Say you want there to be a process where like a jump happens of like three steps up at once. No, that would actually be possible, but the point is that only basic step transitions are possible, where you can just add a number or reduce the number of one of the values. And so if you want to do like go from any number to 0 or any number to a particular state, that's currently not possible with this. And so I just asked Google AI Studio, I gave it the simpler code and said, okay, here's a simplified version, let's go from here, use this code to move forward with, and can you incorporate the possibility of a birth-def catastrophe process or something where there's transitions to a particular state? Okay, and it came up with this code. And the basic idea is that before, the transition class had a rate function and a change and a rate function, and the change was just a tuple with a +1, or like say +1, -1, or two numbers, like an addition to be made to the value of each of the two variables. Okay, and so it came up with this new way of doing it, where instead of it just being a tuple, the update rule can now be a function as well. But it also says it has backwards compatibility, so if you put a tuple in there, it'll still recognize it as it previously did and use it as it previously used it. But if the update rule is callable, if it's a function, then it'll be used as a function. Okay, so now let's go back to the definition of the transitions. So here we have the standard transitions from before, and then here we have catastrophe transitions. These are just simple catastrophe transitions, as in the birth-def catastrophe process, where the catastrophe rate is proportional to the state. And here you can see that in the place of where there was a tuple before, there's now this lambda function. And the lambda function takes x and y and p, doesn't use p. And so in the case of where x is going to 0, the output is 0 for x, and y is kept where it is. So that's why it needs to be a function, because it depends on where y currently is to what the outcome of x and y after the catastrophe depends on where y was, because it doesn't change. So yeah, and now it uses that to put x to 0 and y stays where it is, and likewise y goes to 0 and x stays where it is in the predator catastrophe. Okay, and then it just combines those two lists into one list, and in the Gillespie algorithm part, state chosen, transition chosen index, apply update state 0, state 1 parameters. Okay, so apply update is a method of the transitions class. Okay, apply update, and it will do new x, new y equals. It defines it as the update function. Okay, so that makes sense. And it works, basically. So I just added a little bit of code to make it do 20 simulations instead of just one. If we have it going just one, then it looks something like this. Let's do a few more. And okay, it's different every time. Ah, yeah, because it was using a fixed seed, for the random number generation, but I just included something to make it random again, make it different every time again. Okay, and now the same thing again. I took all of this code and put it into Claude and just said, make this simpler, because it's it's kind of complicated, and so it was 156 lines, and it went down to just less than 100 lines. And so you can see it took the definition of the transition rates from 2 arrays down to just 1 array, because at the end of the day they were just being added together, so may as well just write them as one. And I think it's simplified how the simulation is actually run as well. And it does the same thing. Good. So now we have some code where just by writing these transition class object definitions, you can define any two-dimensional Markov process, continuous time Markov process with catastrophes, or with any arbitrary type of transitions. So that's pretty cool. Now the only real step to go from this to some sort of basic web page like this is we need some kind of user interface where the user can, say, write or press some buttons to define the transitions. There needs to be some way of transforming the user input into something of some code of this format. So that's a problem to think about later. I haven't thought about that yet, but it looks like it's going to be not too difficult, or tractable at least. Okay, and so this is a good point to be at now. Maybe next time I look at this, we'll go from here. But I thought, why not? Let's just have a bit of fun and try and go a couple steps further. And so from this point, I went in 2 directions. So put this code into Google AI Studio and said, do this extra thing, and then put the same code in again and said, do this other extra thing, and that gave these two codes. So the first extra thing was, instead of it being 2-dimensional, let's make it n-dimensional. And so I haven't minimized the code yet, but it did seem to find a way to make an n-dimensional version. I haven't properly understood how it works yet, but this is just 3-dimensional herbivores, plants, and predators, and catastrophes. So that's cool. I still need to minimize this and see how it works, but that's for next time. And then I gave it some code. I gave Google AI Studio some code that I'd written in the past to do variable, inhomogeneous models where the rates vary with time. And so this is a bit different because you can't use the Gillespie algorithm. You need to discretize time, similar to how you would solve an ODE. So I just had some code lying about that did that for what I call the logistic speciation model, and gave it that and said, can you take what you've made already and make it so that any of the rates can vary with time, and stop using the Gillespie algorithm and start discretizing time. And yes, it did do that. So this is just the logistic speciation model. So I'm doing one at a time. And it's defined as a two-type process, but I just changed the transitions so that it only varies in one of the variables. I was just trying to make sure it works and does the same thing as what I would expect it to do, and it does. So that's cool. Yeah, so we have this this kind of nice piece of code to define any two-type process not varying with time. Then we have a time variable process code, and then an n-dimensional version of the code. Right, and so from here, the main steps forward are in creating the UI, and for that it needs to be in JavaScript, and so this is currently in Python, and so we need it all in JavaScript. And so I just put it into Claude AI and said, hey, can you write this in JavaScript? And it did. And so here's a HTML document with some CSS styling, and then there's the script tag, which makes a chart.js display of the result, and all the code is basically working in the same way. So there's the transition class, and okay, so this is just this is actually from before incorporating the catastrophe thing. This is just when change is a tuple and not a function. But in principle, it should be easy to do the same thing with the more complicated version. Right, so yeah, Markov transitions is the transitions, and run simulation. So it gets the parameters from a document.getElementID. So there's like a text input. Okay, and then chart gets the data somehow. Predator data, prey data. Is it definitely using the Gillespie algorithm? Results. Simulation. Gillespie simulation. Right. Okay. So there's the Gillespie function. Yeah. Funny that it's using math. Oh, seeded random. No. So the random number generation is actually a function that's defined. Is there not a math library in JavaScript to get random numbers? Okay, yeah, so that seems to work. And then just uses chart.js and makes a chart. And then I spent some time with ChatGPT figuring out how to animate the chart, so it like shows us it like looks like it's generating in real time. So let's just have a look at what this came up with. Yeah, so I used ChatGPT to get the code to make it go from left to right like that. Okay, yeah, so you can change say the birth rate of that's the prey birth rate. If we change the predation rate a little bit, so now it just dies. smaller. Yeah. It's a bit of fun. Is it different every time, or it's, no, it's a fixed seed? Okay. Okay. Pretty cool. Pretty cool. So that's where I am so far. The next step is to figure out some way of making a UI to incorporate the so the user can add their own transitions. And I was thinking, wouldn't it be cool? Just some ideas. Wouldn't it be cool to also make another plot, which is what's the phase diagram, where it's instead of the populations with time, it's like the X population and the Y population, like the predator population and the prey population. So it's circles around in a random way. And then the other thing is that it would be good to have like a download the data as a CSV. So if somebody wants to like compare their like analytical formula to stochastic simulations, and they want to plot the two together, then they can download the CSV of this and then plot it in Python with their own formula. And then also I'd like to have a feature where you can run like 100 simulations at once, and it plots them all on the same plot, but most of each individual simulation is has a low opacity, so it's only very faint. But then there's also a bold line, which is the mean. And I have some code lying about that's good for taking like a collection of stepwise data and generating a mean out of it. So I can finally use that code, which has been lying about for a long time. So that's it for now. This video is probably reasonably long by now, so I'll just stop it there.